Yeah, so this is the phase period. I think it's dominating in the x direction. You can see how like the model is vibrating in the right direction, in the x direction. And I can stop and check the second mode, and you can see that the second mode is dominant in the y direction. Also, if you want to see all the model results, I can go to here, display tables, and you just have to choose this think structure output, your model information, and you come here, model load participation, model participating mass ratios, and yeah, and you click OK. Yeah, so when you do that, you can have all the results of the model analysis. You can see the first mode is 0.74 seconds and is dominant in the x direction. The following one is 0.65 and dominant in the y direction, and the third one is a kind of like, because it is 0 in both sides, so it means this is a torsional one. This is due to the torsion. You can see that the mass participation ratios, they are all reaching 0.99, which is like which is good, because I think the lower it should be like, should reach at least 90% or 95% of the total mass. So we are now we just saw that there's no problem in the modeling. You can also come in the deformed shape. As you saw, I went here and I can see that how like my breathing is behaving when the dead load are applied. You can see that there is no parts, all the parts, they are all connected to each other. There's no part like vibrating on its own, which shows that the modeling is correct. Again, also, if you want to check if the modeling is correct, you can come here on analyze. You show the last run details, and you just have to check these like eigenvalues, negative eigenvalue. If they are 0, it means that the modeling is correct. So I think now we are done with modeling and checking if the modeling is correct. I think now it is time you can go ahead and define well in the load patterns. You can define where the earthquake loads. Now can you go inside? So before we decide on what to do with this earthquake loading, I think it's better that we just know which method is advised by the codes to follow. Like for this type of breathing, what method can we use in the analysis or in the design? Because there are several methods that can be applied, so we should follow the guidance of the codes. And of course, in our example, we are going to do like a linear analysis, so that method should be like incorporating like linear analysis methods in the procedure. So in order to decide on that, let's check first the code. So in the code, what they suggest is I think in this table 4.4, this is for the table that shows that you come and check if your breathing can be designed by using this method, which is called the equivalent, normally in English it is called equivalent lateral force method. So if you want to apply it on your design, you have to fulfill all these conditions. So your breathing should be like in this. This is the perimeter sum sniffer, which means like classes for earthquake design. So these are the crucial ones, these are the lightest one, and they are saying that you should not have any irregularity in terms of like torsion or torsion irregularities. They should be limited up to 2.0, or maybe this B2 type of irregularity. So if you don't have that, and your building height class bina yükseklik sınıfı is greater than 4, you can apply this method. Otherwise, if your building is not in this table, you have to apply another second method, which is called like mod birleştirme, I think. Yes. So in our case, we only apply earthquake load equivalent lateral force method, and to check on this, like what is the building height class of our building, what is the classification of our building. Let's go again in these tables and see how we can define that, and we can check the earthquake levels as well for our building. So I think in order to define where the earthquake level is, there are values we need, like SDS value, as you can see from here. So in order to get the SDS value, you get it from the interactive website AFAT. You just have to choose the location of your building, and then you can get the spectral values from that website, and then you can decide on what DTS class your building is situated in, and then you can choose the building head class. You can choose the building importance factor. You can choose also what type of method we use in the analysis. So let's go ahead and go to the AFAT like website and do the logging, and then we can. So I'm going to go ahead and log into the EDFLET website, then it will direct me to the interactive website, and then I will come to show you how to perform how to get those spectral values. Yeah, so now I just like did the login in the website. Now I'm going to click here and it will direct me to the AFAT website. So as we talked, like I chose the location of the building to be in Czech McCoy, so I can come here to Czech McCoy. Our campus, I think, is somewhere around here, if I'm not wrong, right? Yeah, it's here. Let's say it is in our campus in Istanbul. So I come here and I click on Raporama and call the name of our spectrum we are going to take, and I choose the earthquake level, which has to be DD2. DD2 is the standard for most of the residential buildings. And then let's assume the soil type is ZB, and then if you want to choose the location of your building, you either have to read the coordinates here, or you can choose to pick a point from the map, which I'm going to choose. So let me say it's somewhere here in the campus, and then I click on calculate, like the hesapla. So when I do that, a new window will open and give me the spectral values I want. So this is a small report involving all the things we need to carry out our analysis. So this is the SDS value I was talking about, and the SS value and this one values. All these values, we need them for defining our earthquake load. Here also is a spectrum. This this is actually this spectrum I use when you are carrying out other types of like analysis, like the one I was saying about the mode Bileşme yöntemi. So this one you just have to download it in Excel, and then you can transfer it to SAP2000. But in our case, we don't need to download this, because automatically SAP2000 we can create this easily for us. So as I just found SDSRU, let's go back in the Excel file and find from the table 3.2 and find which class, like which earthquake design class our building is in. So we saw that our building has 0.669, which falls in this range. So which means that our building is between this DTS2A and DTS2. So to decide which one, you have to check first the importance factor of our building. So as our building is a residential building, its importance factor is 1, and the usage class is 3. So if the usage class is 3, as you can see from here, so the DTS should be 2. So if the DTS is 2, we can easily come and check also again the building height class. The building height class also, it is defined in different. So our let's first find our DTS, which is like here in this column 2, and to find about like our building like height class, let's first we have to first define the height of the building, which is 13 meters, right? And 13 meters is here, right, in this range. So our building height class is 6. So after we define that, also we can define this as well. We can check like what kind of like design method you can use. Here they are talking about the Animagoreta Sarim, which is like strength method. Or strength method means that like you have the rods and you have applied like load factors, you know, in the combinations, and your materials also you divide them by some factors. So you check, like you have to make sure that the capacity of your building is higher than the load that are being applied to your building. So that is the method. That's how the method works. So which is what we are going to do. It's a linear analysis. And maybe if you are doing like trying to attain some performance, for our case DTS2, make sure that, and also the DD2 standard, you don't like the level should be like here, which is like control hazard, or maybe this is equivalent to life safety in English, in the English code. So if you don't so this should be like your maximum level. You should control all the damages to reach to this level if you want to reach certain performance level. So we conduct a DGT approach, which we have already started. So now that we know our building head, the design class, everything, I think now we can go ahead and use that information to define if we can apply really the equivalent lateral force method to our building. So our DTS is 2, and our building is base is 6, which comes here in this row. Immediately you can see we can, because here is 6, so 6 is greater than 5, so immediately we can apply the equivalent lateral force method without any doubt. So in short, like this method is what it does. One second. So in this method is we just have our breathing. Well, let me try to do it here. This is what actually which is shown here. So we have our breathing, and the program will just assign the earthquake rods like proportional to the height of the breathing, and then at the end it will come with like a base shear, force at the end. So in our case, we are going to define those like parameters for the earthquake, and then the program will tell us the base shear automatically. So let's go ahead and do that in SAP. So we just saw that we can apply this method. I don't think now the only thing remaining is to define these points. So as you can see, like SS, I come here and I check the SS value from the thing we got here. SS 0.743, 0.743, and S1 is 0.214. The long period, transition period, actually is 6. I think if you click here, you can see that. Here they are not showing it, but I think when you do like detailed report, they will give you they can show you that value. I think it's somewhere near here. You can see TL is 6, TL is 6, TA and TAB they are given. So this is 6. We assume that our site class is ZB, and this eccentric ratio should be 0.05. This is actually also advised by the code. If you assumed like a rigid diaphragm, so you should at least like apply this eccentricity at least of 0.05 to your breathing. And you can see that when you assign this value, the program goes ahead and calculates these values. Again, also the response modification factor error, we have to check from the code what are the exact values. So in the code, what do they say in the table 4.1? So the response modification factor for our breathing, I think, should be this one, A11, which says that if we are using like high, how can I say, high duct, your system is very ductile, and it is like composed of like beams and columns. Your bearing system is composed of beam columns only. You can use error factor of 8, and this is the overstrength of 3, and also if your height class is greater than 3, which is correct. In our case, it is 6. So also we have other cases where they are talking about if you have like couple beams, if I'm not wrong, and you have like shear walls, you can use these error factors. So normally this error factor means like if you are going to make we are going to follow the rules of ductility. You are going to make your breathing to be ductile. So the engineers suggest that if your breathing is going to be ductile, it is allowable to use an error factor, because this error factor is divided by the acceleration. Is divided by you find the total like seismic load, and you divide it by the error factor to get like the actual earthquake load that you apply in the breathing. So this is like also called like a reduction factor, because they allow you to use like small loads of earthquake loads because they are assuming that your breathing will be more ductile, so it will be deformed. And so if it is deformed, it can sustain too much like lateral forces without necessarily losing too much of its strength. So it is allowable. That's what ARA stands for. So this is also the overstrength, which is the overstrength also is something like that has to do with the excess strength in materials. So also, if I can explain a little bit on that, is we normally, like, let's say for steel, we have like steel defined like this. Normally in the steel properties, stress and strain properties. But when we define the steel material in the program, you just only define this part, the elastic part. But we also have like a high amount here, right? The maximum stress of the steel actually goes up to here, but we only consider this part. So it means that in reality there is some excess of the material strength, but we didn't consider it. So this D factor actually stands for that excess, the material excess that we didn't consider. So yeah, now that we just decided on the error factor and D factor, we also saw that the breathing importance factor also is 1, right? I. So I can come here and already there are 8, 3 and 1, so I don't have to change it. Also, I have to decide on the time period. You can choose either to calculate on by hand and insert it here, or I can choose also to use like the one from the program, but to do that I have to first to direct the program, like which kind of coefficient the program should choose. So to do that also I have to come and check in the code. So in the code, when you come to this table, on the 4.7 section, they are saying that if you have like beams and columns as your bearing system, you can use CT as 0.1. So in our case also CT is 0.1. So yeah, this is correct. I'll use 0.1 to calculate the period of bearing. So also there is another condition we have to control, this one, which says that your period that actually the program, like the period that we saw earlier, was calculated by the program by using this formula. So the period we got by this formula, they are stating that it should be it should not be greater than 1.4 times the one we get by this formula. So I think from this one we got the period around 0.74 something in the x direction. So let's calculate this one and see how much we get. So CT is 0.1 and HN is the beating height, which is 13 to the power 3 divided by 4, 0.75. We get the period to be 0.68, so I multiply it by 1.4 and I get 0.96 seconds. So the period we got from this formula, actually, because it is not bigger than this one when you times it by 1.4, so we can still use this one, the one from the computer, right? So I can still go with the one calculated by the program, and then I click on OK, and I come here and I modify this also. So this is 0 point in the y direction, This is 0.743, and S1 is 0.2, exactly 0.214, and I think all the other things are the same, right? And I click on OK. Okay, so now we did like the definition here. I can run the analysis, but this time also I have to include these ones, and we can see how much the earthquake load we get. So first of all, let's check how the earthquake load they are being assigned. I think you can see now that, let's see the animation. So this is in the X direction. Remember that what we choose. So this is like exaggerated behavior of the earthquake in that direction. I can try to show also the Y one. Let's see the animation. Okay, it's in the Y, so this is correct. Also, let's try to check from the tables like how much is the base shear force, right? Because I think it is very important. Can come to load pattern definitions, auto seismic loads, and I choose these ones by the 218 earthquake load, and I choose the load pattern to be only the AX and the EY, and I click OK. So now you can see like all the things. This is the periods, if I'm not wrong. I don't know. So you can see the base shear in the X direction is 98, and in the Y direction is 100 kilonewton, and this is the seismic weight that was being used. Okay, so that is the all we have. So now I think I can go ahead and do some checks, maybe, where I can find some combinations, and we can check like how our breathing is behaving. So to define the load combinations, also you use the combination suggested by the code, and the code actually just suggests that you use these two load combination, because we have earthquake in our as one of the loadings. So we use these two, and inside these have like, this is, I think it's snow, and you not calculate the snow load in our building, so we don't use this one. And you have ED, horizontal. This is the horizontal component, which stands for these two, and you have the Z component also, which goes here. Yeah, so we are going to try to define all of these. So you can see that there are some alternation here, like when you consider for the X direction, you have to take like 30% of Y. When you consider like the Y direction, you have to take some percentage of X. So, and you change the signs because you are not sure like exactly from which direction you will have your loading coming from. Actually, when you do this definition of the combination, you get like a long list of combinations. Like I can show you here, like here I have a table when you develop all the combination, this is what you get. Like you have this one. This is actually used when you are trying to check like the serviceability limit state. Like can really the breeding like sustain all the gravity loadings by itself, and you check like the diffractions if they are correct or they are in the limits. And then you have this one, you when you open all those, like by using the negative and the positive ones, you will see that you will have like around 22 load combinations. We are going to try to do like the first ones, and then we check the analysis and the plots in using those first ones, because like it will take too much time to deal with all of these one by one. So let me do the first one, like G. I think it will be better to check here, G plus Q plus the horizontal portion and plus 30% of the 30% of the vertical component. Also this one is new in the new code. Normally before they didn't consider like the horizontal component of the earthquake, but this time they consider it. So let's go ahead and first define the G. The G stands for all the dead loads. So I have to add this one and the side superimposed loading, and I have to add also the wall load. So all of these, they compose the G. I have to also to define the EZ, the vertical component. So the EZ is composed of G, as you can see. Sorry, it's composed of G, but the factor is 2/3 times SDS, and SDS, we saw that SDS is 0.669. I'm going to do it in my calculator, 0.67, and I times 2 divided by 3, and I get 0.446. So this is the factor to use for the EZ, 0.446 or 0.45, and I add it here, add. Okay, and then I go ahead and create the first one, which is G plus Q plus EX plus 0.3 EY plus EZ. So this is the first combination. I click on add. So I have to add G, one coefficient, Q. So Q is live, so you don't need to do many things. So live EX1 EY, but with scale factor of 0.3, add, and EZ if also 1 as the factor. So this is the first combination. Okay, and add again, let's say add copy of combo, because I don't want to let me first copy this. So add copy of combo, I put this in here. So here I can only edit, so in this time I can go with, like, let's take minus this UI. Here we put like a minus. A minus here, and I click modify. See, it is updated, and I change it here also. And I click OK. I come back here and I check again, and yeah, it's okay. So we have to, let me try to do like add copy again. I paste this, but this time let me do UI. Yeah, EY and then 30% of EX. So I have to change this. EY should be 1 and 30% of EX, and I click modify. Sorry, EY is 1, modify. Okay, this is correct. Click again on add copy. So this time I'm using like minus EY. Sorry, this is EY EX. So here I'm using minus EX. Click on modify. I think now everything is correct. Okay, let me create like the last two and then we are done. Add new combo and add copy of combo, and I click on Control V. And in this case I'm going to try to do this one, the second one, right, where we have like negative EZ. So I come here, I do 0.9 plus G plus E. We don't have Q in this one. EX plus 0.30 of EY minus 0.30 of, so this is only naming, like the actual editor should do it here. So G should be 0.9, right? Modify, and don't have live, I remove it, and EX is 1, modify, EY is 0.3, modify, and EZ is 0.3 as well. I click on modify, and then I click OK. But the EZ is minus. Modify, OK. I say here and I say add copy, 0.9 here, but in this time I'm going to make like EY minus. So the EZ already is minus 0.3, and Q, we don't have Q. I have to just change this EY to minus. I click modify. Now I think everything is correct now. Okay, so these are the load combination we have. So let's go ahead and check the moments everything. We can also start by checking like, let's also create like one more combination, G plus Q, right? This one is very used, like to check the serviceability limit state. G1 and Q1 and live. Okay, yeah, I think this is fine. So maybe we can try to check like maybe the contours, like in case you have let's try to check like the formation in Z, right? The diffractions. So click apply, and here you can see they are showing me all the diffractions in Z. Let me put this in millimeters. So you can see that the maximum diffraction we have under the G plus Q combination is 1.0 28 millimeter. I think it's the reason why you are having like very small the reason why you have like very small diffraction. This is like -2. It's because like you saw the slab thickness is 14 centimeter, and for such building I think 14 centimeter is actually like a large number. So yeah, there are many things you can check from using these properties. We can also come here and try to check the, let's check the moments under this combination, this one, and see if they make sense. Let's put like in the X direction, try to maximize the view. So yeah, normally you know that when you have earthquake loads, you should expect this kind of loading in this direction. And let me put back in kilonewton meter. You can see now that we can see all the values we have for these kind of things. Like for this column, you can see that the maximum moment it has 46 kilonewton meter. You have the shear values, the diffraction, everything. Yeah, we can check also the actual values. Maybe let's check it in this one. So these are the maximum one. So the maximum is around 566 of kilonewton as the actual force. Actually should be, yeah, so this is the maximum, the actual loading we have. I think now that we checked all of these things, I think we can also even go ahead and do another check, like from the code. I think in the code there is like this criteria which is given, like if you have like some loading like that includes like the earthquake, also you should check like your columns dimensions if they satisfy these conditions. So you have to check like the you have to check like the NDM. NDM is the actual loading, and you divide it by 0.4 times FCK, and FCK is, in our case, is 25. So 0.4 times 25 is equal, this is 10. So I think if I could try to give like small demonstration very quickly, you just come here, you display the, let's took the results, and in our case we want like element output. We want to select the columns, but before I open the table, let's first select the columns, right, using properties, because I'm going to check like that condition on the columns, right. I choose all the columns, select, and I do Control T where I come to display tables. So in our case we are going to check for elements, frame output, element forces, which are for the columns. We want to see the actual loading, and I come and choose, why is not selecting the combinations. Yeah, so in the load case I come and check the ones that have like the combination that have like the earthquake inside of them. So these are the ones, and I click OK, and the load pattern should be all of them. Okay, and then I click OK. So we have a table showing us all the things. I can export this table in Excel. So it is opened. So as you can see, I just have all the columns, all the results inside inside here. So I can easily do the checking by coming here and do the checking. Actually, there are other checking that should be done, but at this time I think now we can run the analysis again, and after the analysis we can run the design, because I think it's very important that before you run the design you have to run the analysis. That's how when you want to do the design, you come to design, concrete frame design. You first choose the combos you want to use in the design, and let's select all of this, the ones I defined, add them. You add them here so that the program will be based on that to do the design. Also, you have to uncheck this. If you don't do it, the program will also add some like automatically generated load combination from the code that is selected in the preference, and we don't want that. So we just want to use the combination we did define on ourselves. So you do that, and then you click here design, you come here design, and you do start design. Yeah, so now the design is complete. Let me put the in meters. So what we are seeing here, they are the reinforcement area. Let me try to zoom a little bit, maybe so you can see. Actually, these are the, I don't know why we can't see well, but these are the reinforcement area. So if you remember, like this is how the program does it. It gives you the reinforcement on the top and the bottom, in the middle, and on the edges, and for the columns it gives you like also the percentage, the areas. So I think now you can see that like there's no anything that is reaching on one. Also, you have the option to come here on concrete, and you can set the design info. So here I can either choose to see the reinforcing, the rebar percentage also is an option. So you know that like you can see that the percentage actually is really low for all the beams and columns, everything. And for the columns to provide like the minimum percentage. Yes, it is 1%. I don't know. Yeah, it's 1%. So which is still like, which is the minimum, of course. Let me see on the 3D view. So the reason why we are seeing like this red for the slab is because we didn't do anything about slab design. So now I'm very curious about, I don't know which. Yeah, so all these are the reinforcement, the percentages. So the next step here is to do the detailing. So because you know the percentage and you know the so you can easily select if I know the area of the reinforcement, I can come here and select how many of reinforcement I want on this side, what and what, and then I can do the detailing. And that's how the analysis is done in SAP2000. And I think this is the end of the seismic design on this story. on this breeding. Yeah, so it was like a very simple example, and it was demonstrative purpose. So yeah, I think it was helpful. So anyone who has any problem regarding the design can always reach out to me about any matter. So of course, yeah, here there are many checks that are being like recommended by the code that we didn't do, like the story drift. We didn't check them. We didn't check the torsional irregularities, the weak story irregularities. So all those irregularities, the second order effects, all of those, they should be actually like checked like before even you do the design, I think. So if you don't like satisfy even one of those checks, you have to either change the structure or the design of your structure, or you have to increase the number of reinforcement maybe, or you can change the dimensions of, you can do the sizing of your members. So you have many options to go through when you find like you don't fulfill one of the checks in the code. So maybe another time, yeah, we can go through those checks if the time is available. So this is the end, and thank you for your attention. See you in the next one.